Well, Happy New Year and welcome to 2021. To get this new year started with a bang, we have a special bonus sneak peek into one of our other programmes for you this week. In our Naked Astronomy series, one of the sector's leading lights joins Adam Murphy and Ben McAllister each month to probe deep into their field of space science. And most recently, dark matter went under the microscope. Now, if you enjoy this show, you can sign up and get all of the previous editions at nakedscientist.com/astronomy, or you look up Naked Astronomy wherever you get your podcasts. And if you appreciate and enjoy the programme, do please consider becoming a supporter of The Naked Scientist. Your donations really help. nakedscientist.com/donate.
Welcome to Naked Astronomy, a space science podcast from The Naked Scientists. This season, we're tackling the big questions from our very big universe. That means that each episode, I, Ben McAllister,
and I, Adam Murphy, will take a look at one of the biggest cosmic questions in the world of space science and astronomy today.
We'll break down the basics for you and then pull in an expert guest for a more in-depth chat.
Last month, we spoke about something pretty down-to-earth, the Square Kilometre Array, which will be the biggest telescope ever built by human beings when it's complete.
This month, we're diving into something a bit more out there, a bit more mysterious, but funnily enough, something very close to my heart.
We are going to dig into the question, what is dark matter? Our listeners may not know that you're something of a dark matter expert yourself, aren't you, Ben?
That's right. For anyone who doesn't know, I'm a physicist, and dark matter detection is the very thing that I spend most of my days working on.
Of course, we won't be answering the question, what is dark matter, because, as we'll discuss, nobody knows.
That's right, it's the reason I still have a job, but we've got a special guest expert coming on a little bit later to take us through some of the deeper details.
And that's pretty awesome, quite frankly. That speaks to the potential that we could be in a golden age of a further, deeper understanding of our universe. That's what dark matter represents.
But before that, Ben and I are going to break down the basics of dark matter. What we know about it, how we know about it, and more importantly, what we don't know about it.
That's right. Feel free to get in touch with us along the way on Twitter at Naked Astronomy or at The Naked Scientists, or leave us a comment wherever you're listening. But without further ado, let's get into it.
Right, well then, I suppose the first place to start, Ben, is what exactly is dark matter?
Yeah, I mean, it's an important question. If we're going to talk about dark matter, great question, what is it? The thing that makes it hard to answer is that we don't actually know the answer to that question. Nobody knows. It's the whole mystery of the whole thing. I mean, we know it's out there, we know there's heaps of it, and there's a lot of work being done to try and figure out what it is. But before we get into talking about dark matter, I find it's often helpful to talk first about what isn't dark matter, what is the regular matter, because people tend to get confused, like, oh, dark matter, is that black holes, is it antimatter, are they separate things, related things, whatever. So let's start by defining regular matter.
Right, regular matter then is all the things like people, planets, stars, black holes, astronomy podcast hosts, all that kind of thing that's made up of just a handful of fundamental particles, which we call regular matter. But what exactly is that breakdown into the universe of regular matter, dark matter, and that other thing we hear about, dark energy?
Yeah, right. So, I mean, the shocking thing, if you're not aware of this concept, is that all that stuff Adam mentioned, people, planets, stars, black holes, that's made out of regular matter, is really just about 5% of all the stuff that there is in the universe, which is pretty crazy to think about. And then about 5 times as much again, something like 25% of all the stuff in the universe, and I'm being pretty loose with these numbers. The exact numbers are like not this nice and round, but this is roughly about 25% of all the stuff in the universe is this invisible, mysterious stuff that we're talking about today called dark matter. And I know what you're thinking, 5 plus 25, okay, that's 30. What's the remaining 70% of the universe? And yeah, good question. That's this whole other thing called dark energy, which we aren't even going to talk about today. We'll probably touch on it in a later episode, but yeah, I mean, right now we're focusing on the stuff called the dark matter because both of those things, dark matter and dark energy, are like huge mysteries that we don't know much about, but at least we know a little bit about dark matter, and we have a few kind of threads we can pull on to try and learn more. So, well, I guess that's a good time to segue. We know a little bit about dark matter, but what exactly do we know?
We know a few things, not much, but a few things. We know that it is out there. We know that we can't see it, touch it, or feel it. We know there's heaps of it. We know there's 5 times as much dark matter as there is regular matter, and we know it's all around us. But that leads into the big question that we're here for. What do we not know?
The main thing we don't know is what it's made of. We have no idea what it is. There's a lot of different theories about what it might be, but ultimately we don't know. And we'll come to some of those theories a little bit later.
Right, well then, how do we know that it's out there? Well, there are lots of astronomical ways that we can figure out little clues about dark matter.
Looking in space at the way stuff moves around, we can infer the presence of this dark matter by looking at the way it interacts gravitationally with the matter that we can see. So the cosmic microwave background, it's a really nice picture of the early universe. It's like in the early moments of the universe, this snapshot essentially of where all the matter was distributed. We can determine a sort of rough distribution of stuff in the early universe by looking at the distribution of this radiation that was left over from that time. The nice thing about the cosmic microwave background is it gives us a really good laboratory to explore the early universe. So we have models of the way the early universe behaves. I mean, there was like the Big Bang, and then there's some amount of matter, and we allow for the possibility of this other stuff, dark matter and dark energy. And then we try and like build a model of the early universe that gives us a cosmic microwave background that looks like the one that we see when we use our big fancy telescopes to actually capture the cosmic microwave background. And what we find, again, it's sort of like an inference thing. We find that we can't build models of the early universe that give us cosmic microwave backgrounds that look like the one we observe without including in those models a bunch of invisible matter that provides extra gravity. So now we need to talk about what we don't know about dark matter, which is, as we flagged at the top, what it is, what it's made out of. We've got no idea.
What we do know is that it can't be any kind of regular matter because of the properties that we know it must have. And that comes down to the four fundamental forces in nature. There is four of them, as the name gives away. That's gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. We know it has gravity because it's the thing holding galaxies together, so that's a tick in the list. And we know that it can't have any electromagnetic force because, well, we use electromagnetic waves, light waves, to see things, and we can't see dark matter, so it can't interact with that. We also know it doesn't have the strong nuclear force, which is the thing that basically holds atomic nuclei together, because if there was 5 times more dark matter than regular matter, and it acted on the nucleus of our atoms, we'd feel it. The thing we don't know about, though, is the weak nuclear force. We don't know whether that's there or not. But what we do know is that it passes through the Earth, which means we can build detectors here on Earth with just a chance of detecting little bits of dark matter.
Yeah, which is great, right? I mean, we don't know whether it's weakly interacting or whether it just interacts through gravity, but we do know that if there is some kind of interaction that we can observe, we actually do stand a chance because we can build a detector here, and many different people are trying to do just that, based on different theories about what the dark matter might be. So there are a couple of different classes of dark matter candidates, as we call them, like candidate theories. One of them is this thing inventively named by physicists as a WIMP, which is a shorthand version of a weakly interacting massive particle, which does what it says on the tin. It interacts weakly with the regular matter, it has mass, and it's a particle. These have been very popular. For decades, people have been searching for a signature of these WIMP particles as they pass through the Earth and interact with detectors. Usually these are big detectors buried deep underground in gold mines, and we'll hear a little bit more about one of those in the second half of the program. It's very exciting. One of the other candidates for dark matter that has become increasingly popular in recent years is a candidate called the axion, which is the candidate for dark matter. Just by the way, I should flag my self-interest here that I particularly work on myself. Axions are really cool because they basically solve two different problems at once in physics. They were proposed not to explain dark matter, but as a result of a completely unrelated problem in physics called the strong CP problem. I'm not going to go into it, but basically some physicists realized in the 70s that you could clean up this problem by introducing a new particle called the axion, and when you looked at the properties you expected that particle to have, they matched exactly with the properties expected of dark matter. So that's another very popular candidate. The two are complementary. People are looking for WIMPs, people are looking for axions, and people are looking for a host of other kinds of dark matter candidates as well. Depending on what you think the candidate is, you have to build a different kind of detection experiment.
And it's good to know that we have the information that Ben is getting paid by Big Axion.
Yes, you do need to keep that in mind. I mean, you have to take everything I say with a grain of salt. It's not so much that I'm getting paid by Big Axion, Adam, as if I can't convince people axions are worth looking for, I'm out of a job. Now that we've spoken about what we know, and importantly what we don't know about dark matter, we're ready to dig into some of the main theories as to what it could be, and the cutting-edge work that's being done around the world to detect it.
Lucky for us, we have a special guest to tell us more. Alan Duffy is a professor at Swinburne University and works in the newly minted Australian Research Council's Centre for Excellence for Dark Matter Particle Physics.
Hey, that's the place I work as well.
It's really an extraordinary situation to be in where you have so little information going in on a candidate, but with such a well-articulated, well-constrained mass range, right? So it really is a situation where it could be within this extraordinary range of mass, and that we all have our favorites, but more or less, I would say the jury's out on where is the focus area. We tend to look for axions, we tend to look for WIMPs. There's reasons to think about these specific candidates, but I'm always struck by the adage of the drunk's trying to look for his keys under the street lamp, and is asked, "Oh, what are you looking for?" He's like, "Oh, my keys." He's like, "Oh, did you drop them around here?" He's like, "No, but the light's better," right? I mean, that's why we look there, is because we can search, and it's not perhaps as bad as that. It could, of course, be in those mass ranges. I think we're in a lot of trouble though if rather than WIMP, it's some fraction, if it's in the range between the axions and the WIMPs, right? So something very, very light mass particles, but still too heavy to exhibit the kind of wave function behaviors of your axions. Then you're in trouble, right? Then you really have a tough time to find. But I think the idea of being quite open to ideas of the candidates is something that sets the dark matter community apart. We have our favorites, but we all keep an eye on everyone else's candidate list because we are fairly agnostic. We really don't have an idea of exactly what it could be.
So I want to start with a question that'll probably annoy two dark matter experts, but how do we actually know that it's there and we haven't just, made a mistake somewhere in all the general relativity calculations, that we forgot to carry a 1 somewhere? How do we know there is dark matter?
All right. Well, look, I think it's fair to say from the astronomy side that the dark matter is convincingly demonstrated as an active component, an actual entity within the universe that clusters, that clumps together, that has structure, because we can see it through the lensing signal, where essentially its gravitating mass is distorting the background image of distant stars and galaxies. Indeed, some of these objects you'll see systems where there's just a dozen stars and they're rotating around in something like 100 million solar masses of dark matter, right? So you can even see by the motion of the visible universe that the dark matter is clearly there, pulled, as it were, by this unseen companion. So from astronomy, we know the dark matter is an active participant as opposed to some kind of a mistake of gravity, right? So we talk about MOND, or modified Newtonian dynamics. Maybe we're just wrong with the theory of gravity in that regard. And I think the beautiful examples of the bullet cluster in particular, that to me was the watershed moment where we would consider the potential for gravity to be a modified gravity to be an explanation. And then I think the vast majority of us realized that was no longer valid when the bullet cluster arose. If it's gravity that's wrong, let's go to a situation where in a cluster, we have galaxies whizzing around, and we found that there was a lot of X-ray, very hot emitting gas in there. So all the mass, in fact, of the cluster is this hot X-ray emitting gas, primarily in the baryon sector. And then we say, oh, look, there's about 4 times more dark matter there, and everything else you can see. The MOND community says, well, no, it's the gravitational theory of that luminous gas that we haven't quite got right. How can we test that theory? Because it's sitting there, the gas is sitting there, the dark matter, I would say, is sitting there. So their gravity is indistinguishable, as it were. So the beautiful scenario is when you get 2 clusters collide together, essentially the gas slams just like a pancake, just goes squish. It has a huge cross-sectional area. It just goes bang. But the galaxies, relatively speaking, are small targets. It's fun to think of, but on the scale of a cluster of galaxies, a galaxy itself is a tiny entity. They just flew right through each other. So essentially you have the galaxies flying completely through this collision, and the gas remained splattered in the middle. And then you say, well, where's the gravity? And how do we look for gravity? We look through it for gravitational lensing. So when we look at the lensing signature, literally the optical distortion of background galaxies and other objects by these clusters, these colliding clusters of galaxies, where is the lensing signal concentrated? If MOND is right, and that it's just some kind of change to gravity, and most of the mass that would produce that gravity is this gas, then the lensing signal should remain there. And if dark matter is right, then the dark matter will also, very similar to the galaxies, be collisionless. It will have just gone through the collision without problem, and it should be hanging around near the galaxies. And indeed, where is the lensing signal seen? Around the galaxies. There was a collisionless component that made it through the collision and indeed revealed that still all the mass is there. And perhaps an even better example than the bullet cluster is the fact that you have systems with lots of dark matter and systems with very little dark matter. And that's actually the fact we think we saw a galaxy with almost no dark matter. That's actually a great example in the favor of dark matter, because the modified gravity would never allow you to do that, right? If you see a million stars,
It should be the same everywhere, right? If we're changing the rules of gravity.
Exactly, that's right. So if you see a million stars in that galaxy, and sometimes, then you'll see a certain amount of gravity from modified theories of gravity. If instead it's got lots of dark matter, which we've seen systems like that are dark matter dominated, we've seen systems with very little dark matter. That kind of range of dark matter fractions actually speaks to the fact that dark matter is real, and that it's not just a simple unified change to gravity, for example. But by this point in the journey, it is absolutely a new particle. And that particle, as I say, could be a primordial black hole. And in fact, we've got a few more nights in the can using DECCAM, a big 4-meter telescope out in Chile. And we're actually looking to see, can we now rule out even the primordial black holes idea? Because they will move between us and a background star and cause a brief magnification, a lensing event, a magnification, a brightening of that star. So if we look quickly enough, often enough, we may see those tiny primordial black holes move between us and those stars. And if we don't see them, then that will set a limit to how much of the dark matter could be in the form of primordial black holes. And we're really pushing now to just rule this out completely, leaving only a new particle as the explanation. And that implies an entire new field of particle physics beyond the standard model. And that's pretty awesome, quite frankly. That speaks to the potential that we could be in a golden age of a further, deeper understanding of our universe. That's what dark matter represents, to push the models to an even greater understanding of the foundations formed in those early fractions of a second after the Big Bang. It's a really exciting time.
So we were talking about like primordial black holes and the telescope work that you're doing to detect them or rule them out, which sounds like a great time to segue into talking about some detection ideas for dark matter. Because we've talked about these different candidates, these very light axions, these medium mass WIMPs, and the really heavy comparatively black holes. How do we detect dark matter? I guess is a pretty broad question.
So you can find dark matter either by production in the lab, so at the Large Hadron Collider. So you would form it in a high energy collision. And what you would see, you would track the amount of energy going in, and you would track the amount of energy going out that was detected by your incredibly sensitive detectors all around the collision site. And if there's a small amount of mass difference that you're not able to account for, that tells you that something that doesn't interact with normal material has just escaped out of your detector, and that could be the dark matter, right? So as far as I'm aware, that's not being seen. Or you can wait for it to hit your lab. And thankfully, because the sun moves around the galaxy, we move through a cloud of this dark matter, and informed from simulation, informed from astronomy, we know roughly how much dark matter there is. So you pick your favorite candidate dark matter. In other words, what mass does it have approximately? And that will tell you how many particles are floating around to add up to the amount of dark matter that you see. And with the known speed that you go through it, you can essentially estimate how many particles go through you, and it's hundreds of millions a second. And what we hope, they're weakly interacting particles. So there's a weak nuclear force, essentially this dark matter wind, these hundreds of millions of particles that fly through us every second, that very occasionally they will have a direct collision, as it were, billiard ball, snooker ball style, with either the nucleus of the atom or its electron. And that's very interesting, that case of hitting the nucleus, because you get a recoil. There's an energy transfer. Again, hit one snooker ball into another, you're going to send them scattering. And because the nucleus is charged, what you would see then from this otherwise invisible particle that just hit you, you now have a visible particle that is moving and it's charged. And depending on your detector, you will get a visible signal from that. So that's the name of the game, right? You're waiting for the dark matter, no matter what it is, to hit your detector, and you've set up your detector, hopefully in a sensible way, to record any small amount of signal. The exact way you look for that signal, that's the engineering, right? That's the art. Where we have, for example, SABRE, the lowest background, largest detector in the Southern Hemisphere, hopefully will be installed in 2021 at the bottom of an active gold mine in Stawell, Victoria. That is a sodium iodide crystal. So this is something where we are hoping the dark matter is anywhere from, say, a few times the mass of a proton to 100 or so, 150 times the mass. Very much classic vanilla WIMP territory. And the idea is that it would hit either the nucleus of the sodium component of those crystals or the iodine component, and you would get a recoil. They'll emit a flash of light. We dope the crystals with thallium so that that light is invisible. And we have two very sensitive cameras looking indeed affixed to one of these sodium iodide crystals. And just to paint the picture, it really is basically like a soda stream bottle with rock salt, right? I mean, sodium iodide, I wouldn't be eating it particularly, but it's sodium chloride is what you put in your chips, right? So very, very similar. So it's incredible to look at, to see this, ultra pure sodium iodide crystal. And that's part of the problem, because we're waiting for these very occasional collisions. And now, because of the incredible work of teams around the world, we know, who keep setting the thresholds ever lower onto to how strong the interaction the dark matter has with normal material, we know that we've got to wait. I mean, we're talking maybe a collision a day for essentially 50 kilograms worth of active detector, maybe even less, maybe one a week. I mean, all the while you have local radiation, you have cosmic rays, you have all these other sources of signal that are also hitting your crystals and causing flashes of light that could indeed look like the dark matter. So it's incredibly challenging measurement to make. The main battle for all of these kinds of detectors is control of the backgrounds, to be sure that when you do see the dark matter, it is dark matter and not these other sources.
We love our acronyms in the dark matter community, don't we? I mean, you talk about SABRE, the detector in Australia, Xenon.
That's not just dark matter physicists, Ben. That's science in general. Every scientist loves their acronyms.
I've been part of quite a few collaborations, and I can assure you the very first thing after you all get together and go, should we do something about this thing? And it's like, yeah, we should probably do that. And then we go on an acronym generator on a website, and then we try to figure out a name. And then once we've got the name, then we're off.
Yeah, I mean, I can't talk. My Axion experiment is called Organ, which is a bit of a horrible backronym in itself. So it's definitely a phenomenon.
Take me through Orion, and I want to emphasize everything I've been speaking about, this kind of billiard ball model, right? Where it is just the dark matter is sufficiently massive that it can be seen as a particle, and there are subtleties, form factors, and things where some quantum nature does creep in. Right, we are still talking about fundamental particles hitting each other, but by and large, billiard ball collisions is the right picture for these. But axions are so light that that's not the case anymore. But it's your experiment, right? And with Mike and Tobar over yesterday. So maybe I don't want to do it wrong. Can you tell me about the axions?
I'll be relatively brief, given this is an interview. The subtle difference, I suppose, well, as you've alluded to, yes, the axions are much, much lighter, which means that their behavior is slightly different. We call them like wave-like dark matter. It's almost like we're sitting in this field, this like background field of axions. There are just so many of them in order to make up the dark matter. The thing that's different about axions compared to WIMPs, because they're so much lighter, we don't wait for collisions, because there'd never be enough energy imparted in
a collision of our very light WIMP with a nucleus in order to measure anything detectable. There's just not enough momentum. However, axions have this cool property, or they're predicted to have this cool property, where they can convert from axions into another fundamental particle that we know very well, the photon, the particle of light, and essentially dump all of their mass energy into photons that we can then try and detect. So it's a similar kind of thing in the sense that we've got dark matter just like moving through our detector, or we're moving through the dark matter if you prefer. And you set up your detector, and in the case of WIMPs, you're looking for like a collision with a nucleus that imparts some energy. In the case of axions, you're trying to engineer the right conditions so that the axions convert into photons, and then you're trying to detect those photons. And so that's what we do with Organ. We're looking for photons in the microwave band as a result of axions converting into tiny little flashes of light inside our detector.
Yeah, and bearing in mind that it literally is a microwave oven, right? I mean, it's a supremely sophisticated, but a la quasi microwave oven, right?
Yeah, I mean, you wouldn't want to be trying to cook anything because the levels of microwave field that we expect are very, very, very low as a result of axion to photon conversion. So you'd be waiting a long time for your microwave dinner. But yeah, in a sense, we are catching microwaves in a little resonating box, similar to what a microwave oven looks like, and trying to read out a signal there.
Seems to me that axions just want to shine, and they just want to be seen, so they turn from dark matter into photons, which we can see, just to get the attention of it.
I like that. That's a nice way to look at it. I mean, hey, wouldn't you want to turn into a little flash of light after however many billions of years being a tiny little invisible particle floating through space?
So I mean, look, the thing that I love about the axion idea is that we can learn so much more about the dark matter so much more easily if it's an axion, I think, than a WIMP. Beyond the collision itself, it's rather hard to learn much more, right? Like, in other words, you need a lot of collision. There's not a lot of information in the collision. You essentially be looking for the light. How does the light profile, that flash of light, change and over nanoseconds, or even faster? It's an extremely involved measurement, and it's more akin to the old chemistry experiments where they would weigh up the fractions of a chemical reaction to try and figure out what happened, than the modern day particle physics where you have exquisite information about the exact nature of the collision. Whereas axions are far closer to that, right? You can really play with the instrumentation and really fine tune it once you get a signal detected, of course. Whereas I do think with WIMPs it is a little harder. They just don't do much more kind of collision, unless
they
it's
just
more
bumble along and then knock into something after kicking around.
Yeah. I mean, I'm sure they will come up with clever ways to explore it, and especially if it's got any unique properties. But a lot of this dark matter search is Occam's razor in real time, where you're always resisting the temptation to add extra complexity to your model. You're really talking about the standard vanilla case. Why shouldn't there be an extra particle in the universe, right? There's a lot of mass energy out there. And indeed, in the dark matter sector, with some 4 or 5 times as much as there are of our baryonic sector, and look at the complexity of us. So why shouldn't there be more of the dark matter out there, and many populations or different species in the dark sector? And I'm not a big fan of imagining dark planets and stars and things. I mean, I like the idea of an entity that isn't clumping like that, but I still think that there's something very captivating about that idea. But you just have to remember, we haven't detected anything yet, so we've got to keep ourselves grounded and look for one thing, and then once that's detected, you can see, does it explain everything, or are there more candidates required? And I think that's the moment that will be so exciting when we get that signal, because that's just the starting gun. I mean, every theorist in the world will go crazy at that point and just start to spin out ideas from that one signal. Although, of course, we do have that one signal, I should say, the Dama Libra experiment in Italy, which is the sodium iodide experiments run for over a decade now.
Yeah, fantastically segued, Alan. Please say more about Dama Libra, because this is getting on to one of the last things we wanted to ask about.
Okay, cool. Well, I mean, so I will say that Sabre is designed to test the Dama Libra claim detection, right? That is our raison d'etre. So we have in Italy a detector that has seen what is called an annual modulation. So that is a change through the course of the year of the number of dark matter collisions, or at least something is colliding, and there's more of it in June and less of it in December. Why we think that might be dark matter related is because as I said, you go back to that idea, the sun going around the galaxy, we have this constant headwind effect. So if you've been driving in the rain falls down vertically, more or less. I had a massive thunderstorm near me yesterday, so it was nearly horizontal rain. But typically you will have rain that falls vertically, but as your car drives through it, it looks at the last second like it rushes towards your window screen, right? So that's a headwind effect. In the same way, our sun goes through the dark matter. So we've got this headwind, this flux of dark matter. And for half the year, the Earth is
we're
in the
being
same
dragged through a sea of dark matter as we move like with the sun around the center of the galaxy, and that's like why we see a
Yeah, that's right. That's
effect.
absolutely right. So for half the year, we're moving around the sun in that same direction, more or less. And then for half the year, we're moving in the opposite direction to that of the sun. So when our velocities combine, so for half the year, we're going faster together. So the headwind looks like it blows faster, more particles going through us. And then for half the year, we're going against the sun's direction. So the headwind is slower, less particles going through us. It just so happens that that peak, it is in June and it's opposite in December. You would expect to see more collisions then in your detector in June than in December. And Dana has seen that.
That can be a bit difficult to picture without seeing a diagram, right? I mean, it's like you got to think about something that has two components of velocity. Like the sun is moving in one direction. It's like, okay, that's dragging the Earth. So we're seeing this thing. And then we're like just zipping around the sun as well on our own little trajectory. And then that creates the second component. That's the thing that modulates. So yeah, I don't know.
Yeah.
It's kind of hard to picture unless you've seen something.
Oh, that sounds like it could be the foundation of some like really horrible new variety of astrology, you know, like Mercury is in retrograde and the dark matter is in headwind, so that's why you're having a bad day.
Oh, well, it's in Cygnus is the direction that the sun moves in. So that's where we think the gust of dark matter is. So I fear the moment when the astrologers jump on that and say Jupiter is in ascension in Cygnus, which is why we do whatever, right? But look, we certainly have this claim, and it's beautiful. If you look at the data, there's just this beautiful sinusoid slowly varying across the year, seen 10 years running. The problem is that, of course, the other thing that varies through the course of a year is the seasons. And there's a very real expectation that cosmic rays, these particles from space that collide with us and with the detectors, those also vary through the course of the year. So maybe it's not that we're seeing a signal of dark matter, maybe we're seeing the background of cosmic rays vary with the seasons, right? And that's why you would get this. And one easy way to test that, definitive way to test that, is to build an experiment very similar to Gamma Libra, and that it would be SABRE, sodium iodide crystal, and do a direct comparison, but take it to the southern hemisphere so that in June, their summer, it's our winter. So if there's a seasonal effect and they see more events in June, their summer, we should see more events in our summer, which is December. Right? So that's almost as hard to imagine, I think, for a lot of listeners as the visualization of the Earth going around the sun and increasing the headwind effect. The fact that you can have a hot Christmas. But look, we definitely.
Hey, we're living through that hot Christmas right now, Alan. It's December 18th in Australia, and yeah.
Coming from Ireland, and then when I went to Perth, and it was like, oh man, it was wild. The first summer was so hot. But the idea of if it's dark matter, it's able to fly straight through the Earth. So if Gamma Libra sees an increased number of dark matter particles in June, we should see that as well. And fewer particles in December, we should see that as well. But if it's something to do with the seasons, well, we're 6 months out of sync in that regard, so we'll see the opposite behavior. So it's the cleanest way you can test for this being something astrophysical, so something akin to dark matter. It will be very exciting. We'll be able to test that in just 3 years of operating. And I think that will be a very shocking moment, quite frankly. If we confirm their detection, that will be unbelievable, because the community has essentially been somewhat skeptical of their claim for many years. So that will be a very interesting moment.
As they should be. I mean, that's science, right? We see a claim, we've got to test it again and try and verify.
Yeah, absolutely. And I think it's worth pointing out that a lot of experiments have been run very much larger in terms of detector mass, but different types of elemental compositions of their detector, but nothing quite like the sodium iodide that was used for Gamma Libra. But if you use the same kind of material and you take it to the other side of the Earth, and then you see a signal that peaks in June and drops in December, okay, well then that's going to be very exciting to the world. To be honest, it will be exciting either way. It's getting tricky though, because we are now building detectors of such size that we will at some point, this next generation, in fact, of detectors and the way they're scaling in mass, and sensitivity. We will start to see another weakly interacting particle that does exist in nature, very definitively so, and that is the neutrinos from the sun. So at some point, we will be blinded by the sun. Even at the bottom of an active gold mine, a kilometer underground, we will be blinded by the sun, but not by its light, but by the neutrinos it emits. So then we need a completely different type of detector technology, which is called a directional. So we can basically block out those signals because we know where the sun is at all times. But it would be an amazing thing to have neutrinos forged in the fusion reactions at the core of the sun that travel out across the vast distance of space to reach through the Earth and then hit our detector, and then you treat that as annoying, and then you say that.
Yeah, exactly. The world's most sensitive neutrino detector has all of a sudden, become a useless dark matter detector.
Yeah, that's right. So it's an incredible bringing together of quantum physicists, of nuclear physicists, particle physicists, astronomers, astrophysicists, and engineers, civil and structural and mechanical, all to operate on a scale of detection. It's really an extraordinary field of research that dark matter has become. And I think because of everyone's collective work, we will discover this dark matter in the next 10 years. I'm very confident that. Or it will take us perhaps 50 years thereafter, right? Because it will become so challenging to disentangle it from the background solar neutrinos that we probably just, we're not quite back to square one, but almost.
That's it for this month's episode of Naked Astronomy. We hope you enjoyed it and maybe learned something.
I'm a big dark matter nerd, obviously, and I hope that some of the excitement of the hunt to discover what 5/6 of all the matter in the universe is made of has rubbed off on you.
If you enjoyed yourself, please get in touch with us on social media at Naked Astronomy or at Naked Scientists. Throw us a subscribe or leave us a rating, review, comment, or like wherever you're listening.
You can also get in touch with us by leaving a signature embedded in the annual modulation signal of dark matter passing through the planet.
Also, if you've got a big cosmic question you would like to see us cover, send it our way. You can get me at adam@thenakedscientists.com.
Or me on email at benm@nakedscientists.com or at Dr. BT McAllister on Twitter. Thanks again for listening. I'm Ben McAllister.
I'm Adam Murphy.
And keep watching the skies.
And if you enjoyed that episode of Naked Astronomy, do please consider signing up as a subscriber at nakedscientist.com/astronomy, or you can find it wherever you get your podcasts. And do please also consider signing up to support The Naked Scientists. Your donations really help. And if you can become a regular supporter, even if it's a small amount, it really, really helps to keep the show on the road. nakedscientist.com/donate for more details.